Hello everyone. Today we will look at some case study on how to remove a staple from using a staple remover. This is going to be done through a DFMA approach. We are going to look at various steps that is involved in the making of the optimizing the product using the DFMA approach. The objective is to demonstrate and how to analyze the given product using the design for assembly and the design for manufacture concepts and reduce the parts and the cost of the process. We have already seen what is designed for assembly and what is designed for manufacture. Just to go through the same, the design for assembly is a method of design the product for ease of assembly. How easily you're going to make an assembly is what we're going to look at. And it is a tool used to assist the design team in designing the products, okay, trying to bring down the cost, trying to focus on the number of parts and handling etc, all that. The design for manufacture is a method of design of ease of manufacture of collection of parts that will form a product after assembly. Design for manufacture is a tool to select the most effective material and process. Okay, different processes have different cost, so we're going to look at how we can choose a process that will be much cheaper. Now these are the differences between the DFA and the DFM. DFA is more concerned with the reducing the product assembly cost. It minimizes the number of assembly operations. Individual parts tend to be more complex in design and they tend to bring down the complexity. But the design for manufacture focuses more on design with the reducing the overall production cost. It minimizes the complexity of the manufacturing operations, and probably it is also using common data features and the primary accesses. The sequence to assemble this is to actually look first for the design for assembly and then look at the manufacturing, because when I look at first at the design for assembly, I ensure that the number of products comes down, number of components comes down, and when the number of components comes down, it is directly going to impact the design for manufacture also. Okay, a summary of the design for assembly. Generally, this is what we actually ensure: the minimum part count, design parts which will have self-locating features, design parts which have self-fastening features, more of snap fit, etc. Minimize the orientation of parts during the assembly. Orientation cost time. It takes more time, and then the setup is also will be increased. Setup time will be increased. Design parts for retrieval, handling, and insertion. How do you handle the parts? Emphasize top-down assemblies. Standardize on the minimum use of fasteners. Okay, encourage. First, check whether a fastener is required at all. If it is not required, then you try to adapt that. But if it is required, try to choose the fasteners which are much easier. Is there a way of trying to go for adhesive fastening? Is there a way to go for snap fit? Okay, or do we have to go only for the threading operation, which is a very costly process? Encourage modular design, okay, so that the individual parts can be removed and then put back again for easy replacement, etc. Then design for a base part to locate other components. Design component for symmetry for insertion, right? The steps are like this. Okay, first step one, check at the product information. What are the functional requirements? What is functional analysis you'll have to look at? We have a table as to how you can go through that. Identify the parts that can be standardized. Use basically standard parts. Determine parts that count on efficiencies. Right. Step two is determine your practical part count. Find out how much actually you require, how many number of parts that you require. Check for mistake proofing opportunities. The POCA okay that we or the mistake proofing, that try and concentrate on that, and then check whether you can eliminate mistakes or mitigate the mistakes down. Identify handling, grasping, and orientation opportunities, insertion, locate, and secure opportunities. Also identify and reduce the secondary operations. Further secondary operations of whether is there any machining that is going to be required. If there's a machining to be required, then is there some deburring operation or chamfering operation, etc. Such kind of things. Let us concentrate on that and then remove that. analyze data for the new design, right? Okay, so this is the Cummins, the DFA analysis sheet. Now, if we go systematically step by step for all the parts that has been given here in the listed down here, list down the parts here, and then go and look for design for assembly complexity, look for functional analysis, error proofing, then handling difficulties, insertions, and secondary operations. For all these things, there are subdivided into much smaller activities. Like for example, design for assembly complexity can be made as number of parts and the number of interfaces between the parts. For example, of functional analysis, we can also look at the theoretical minimum part functions that are there, or whether a part can be standardized, or whether do I classify a part cost as low cost, medium cost, or high cost. Okay, now further divisions are all possible. Now once we tabulate for all these things for a particular product, I will be able to give a better picture, and that is the approach that of the case study that we are going to do now. Now, the first thing is that we are going to take the stapler, not the stapler, but the staple remover. Okay, so this removes a already stapled, pin, and then it tries to remove that without damaging the paper or whatsoever. List the parts in the order of assembly. Now, there's a design which is already given. Now, for that design, we're going to do the analysis. Now, DFA complexity, we'll have to look at the different numbers. So, we have listed down the various parts that are there. There is a name for each of the part, and for the sub-assembly. You have the lower arm stub, and then you have the base part or the lower arm. The lower arm cover is there, rivets, and the upper arm. Then the upper arm also has, like the cover, rivet, and the other parts are like the spring and the pivot. There are four different kinds of parts. Okay, now this is how the staple looks like. Okay, when I try and then try to remove disassemble the stapler, try to study and then bring it down. This is how it is going to, the view is going to look like this. The the finger pad. Okay, the rivets are there. Okay, now rivets, why these rivets are required? They are for joining the this part. Okay, this narrow tooth remover to the other one. Okay, there's one narrow tooth remover for the bottom, and there's a wide tooth remover for the top one. So these two teeth are going to go inside and then catch hold of the staple pin which has already been stapled, and then pull them out. Okay, so that is why this entire purpose of this product is going to be. Now, listening for the number of parts, if you start looking at the right hand side between the previous one, okay, and this one, okay, look at this. So, design for complexity, you have these various things, and then we start putting the number of parts. The number of base part is 1, the number of rivets that we are using is 2, and the number of interfaces, or this, the implication of this particular component or with the other component. What is the number of interfaces do they have is what is being written down here. Now, for example, the base part, an arm to rivet, then arm to, there's another arm to rivet, arm to cover, arm to pivot, arm to, spring, and then arm to arm. Okay, all these things, 6 rivet, 6 interfaces are there. So for 6 interfaces, we list down all these interfaces like there in the second column. Okay, stapler removal part count, we can try and bring it down like this. Like what we do is list the parts in the assembly, assign the part number to keep up with the part, list the number of parts, that's called as NP, list the number of interfaces, that's NI, and then I try and go and look at their ratios. Okay, the ratio will be given here, the NP and NI, etc. We look at this, but then before that, how do I reduce the number of parts? Okay. Okay, so we have a kind of a flow chart where there is a current design, right? We start asking questions whether it is yes or no on the movement, on the isolation, and the adjustment or replacement. On this side, we have the current design. Consider the specification and other options. Does the part move relative to all other parts already assembled? Is there a relative motion? If yes, then we are going to ask whether is the movement essential for the product to function. Okay, if again yes, is the motion is definitely required, then we go and say that must the part be separate to provide the required movement. If it is no, then I go and try and join the part. Okay, so that is, you critically try to bring down, question the clearly as to whether this is required or not required, right? So okay, but suppose, let us say, does the part move relative to all other parts already assembled? If the answer is no, then straight away, then it is a candidate for removal, or it's a candidate for deletion. I need not have that part. I can try and combine the two part together. Now, is a part a different material or isolated from all other parts? No. If it is no, is a part separate to allow for its in-service adjustment or replacement? Still, if it is no, then it is a non-essential part. That part is not required at all. On the other side, let us say that, must the part be separate to provide the required movement? If the answer is yes, ask another question as to, must the part be separate to satisfy the different material or isolation? Should it have a different material? Okay. Then if the answer is still yes, then go for the next question. Must the part be separate to enable the adjustment or replacement? If the answer is still yes, then it becomes an essential part. So this is how critically, you analyze the flow chart, ask questions on various stages, and then find out whether this particular part is required or not. If the part is required, then the part will continue to be there. If the part is not required, then you can eliminate the part. If there is no relative motion between the two parts, then you might as well join them into one single part and then bring down the part numbers. Okay, so the same questions that has been shown here. Um, Basically, we have a matrix of questions here where you critically ask them for whether the particular action is required or not, and based on that, you can take a decision whether it is an essential part, it is a non-essential part. Okay. Can the parts be standardized? Yes, this is one question that you should be asking. If there's a standard part, then the cost would come down. Okay. Within the assembly station, yes, or whether within the full assembly, or within the assembly plant, within the corporation, or within the industry, where is the standard part? Okay. So should they be yes or no is what is the answer that you should be asking. So let us say that, the functional design, you say that, is yes. Can the part be standardized? If the answer is yes, then you can go for the standardization. Okay. Now look at this. What has been done here? Now this was the original design and the part, etc. But what we have done here is that these rivets have been removed. We found that the rivets, the purpose of the rivets were only to hold the first two parts. So suppose I use an adhesive and join them together, then I might as well remove the adhesive, I remove the rivets. So I would have eliminated four parts there. Okay, so that is how you bring down the part count. Now here, in order to check the assembly efficiency, theoretical part count efficiency is equal to the theoretical minimum number of parts and the total number of parts. Total number of parts, when you start the analyzing, what is the total number of parts, and actually how many theoretical number of parts. If they both are same, you multiply it by hand, and that's the highest number. Okay, what we are trying to bring down uh, is the in a rule of thumb, the part count we are trying to bring down. What we are trying to say is that the count efficiency should be at least 60%. It should be there. That's a goal. So towards this, we are trying to talk about the design for assembly complexity factor, and the definition goes by this: you take a sigma of NP and NI, and then individual sigmas, and then take a root of that. Okay, this is known as the design for assembly complexity factor. We try and analyze how complex is the design. If there is a component which is complex to be assembled, then you must understand that there is more rejections going to happen. Okay. Now, determine the product cost level. In cost level, we just said that, it should be asked whether the cost is low, medium, or high. Classify the cost, whether it is a low cost one, or whether it's a medium cost one, or the high cost one. Okay. Determine the practical minimum part count. After doing all this team assessment of the practical changes, you have to understand the difference, or you have to trade off between the part cost and the assembly cost. Okay, at one side, the part cost will be going up because you want to bring down the assembly cost. On the other side, if the part cost is being reduced, the assembly cost will go up. So either way, you'll have to see, and then you have to balance it and trade off between the assembly cost and the part